Good morning. Let's see. I've got the first homework assignment posted up there. Please, this quarter, pay attention to the requested format for the homework assignments, and let's work this quarter on beginning to make these things perfect. And so I'm trying to prepare you for even fussier teachers ahead at the university level. Many of you are transferring to there next year, and then eventually even fussier bosses than you'll ever have as teachers. So we'll be working on that this quarter. Anyway, I wanted to start by showing you a series of demonstrations. These are those videotape demonstrations that the guy has, but they may help you with some of the questions that are on the homework. And so if we watch these, there's questions about inducing charges on things. And I finally figured out which vitreous is and which is resinous as far as the charges go. And the guy doesn't use those terms, but he does use a rubber rod, which would be a resinous rod, and then a glass rod, which is vitreous. And he talks about the different types of charge that he gets on those. So anyway, I'll share the screen with those things, and I'll just do that. So, I don't know if you'll be able to hear the sound on these or not. I may just kind of have to narrate, or maybe just crank the sound up on my computer, and it might pick it up. I don't know.
Next, I'd like to demonstrate.
Could you hear anything there?
Yeah.
Yeah, we did.
Good.
Demonstrate and discuss the electroscope. Here's a device. There's a stationary arm, this blue arm, and a removable arm, this red arm. And when we put a charge on this, such as by taking a rubber.
One important thing here is that the two arms are electrically connected. So that wasn't clear immediately, but they do happen to be. So
A rubber rod and rubbing it with fur and getting a negative charge.
okay, so resinous is negative charge.
This, I'll just bring the rubber rod up close and we'll watch what happens. We see that we drive electrons from the top plate down to both the movable arm and the stationary arm, and then they separate from one another, indicating again that like charges repel. As I take it away, it relaxes and comes back. And as I bring it over here, it drives electrons down. Now, if I actually touch that plate with this rubber rod, then some of the electrons, and it looks like a little spark jumped over there and grabbed before I even touched it. Some of the electrons now have been transferred from the rubber onto this plate, and that will cause that arm to stay separated, the movable arm to stay separated from the stationary arm, as the stationary and movable arm both have negative charges on them, and negative charges repel negative charges, and we see the separation is an indication of how much charge there is on the electroscope. Now, if I take the rubber rod and again bring it near, we notice it drives even more electrons down, causing an even greater charge on those arms and causing an even greater separation. Now let's see what happens when I take a positively charged rod, which I can obtain by rubbing silk with glass. We rub electrons from the glass onto the silk. The glass therefore becomes positively charged. I bring that near the electroscope, and that will cause electrons to be drawn up near the top, leaving fewer electrons on those arms, causing the angle to decrease, indicating that the electroscope has a negative charge, and positive charge attracts that negative charge, allowing that electroscope to relax.
Okay, that was the first one. And then let's see. Electroscope Induced Charge. I haven't watched this one yet, but these are short, so.
Next, I'd like to demonstrate charging by induction. What I'm going to do is start with an uncharged electroscope and get a good negative charge on this rubber rod. And again, bring it nearby and observe what happens in that we drive electrons down. Now what I'm going to do is I'm going to touch that electroscope with my hand here and draw some of those electrons off onto my body. So some of those electrons have now been transferred onto my body. Notice I have not touched the electroscope with the rubber rod. What I'm going to do now is remove my hand and we'll observe what happens. I took some of the electrons from the electroscope onto my body, and so therefore the electroscope should now be charged positively. If the electroscope now has a positive charge, then when I bring the negatively charged rod up, let's see what happens here. Now I'm driving electrons again back down from the base down to the arms of that electroscope, reducing the effect of the positive charge on that electroscope, neutralizing it with negative charge, and we see that the arm drops down, indicating that the electroscope now has a positive charge on it. We can reduce the effect of that charge by driving electrons from the top down to those arms. Further, we can then take the rubber or the glass rod when rubbed with silk, and the glass rod becomes positive, and it will attract some of those electrons from the arm up to the top, leaving those arms even more positively charged and causing them to separate even more so from one another, indicating that the electroscope has a positive charge and it's obtained that positive charge through induction.
And then he does something with spheres, and some of the homework questions are talked about.
Next, I'd like to discuss some other aspects of the electric field. Here I have an electroscope, a couple of spheres, and the Van de Graaff generator. I'd like to begin by charging the electroscope negatively by rubbing the rubber rod with the fur, and we find that when we rub fur and rubber together, the electrons get transferred from the fur to the rubber, and we see that when I then bring the rubber rod near the electroscope, that it drives electrons down, causing the arm to move out. If I touch the rubber to the electroscope, then I put some of those electrons on the electroscope, and that arm will stay permanently moved out there until we do something to take electrons away from the electroscope. So now that we have the electroscope charged and the movable arm is standing out, let's show that we have no charge on either of these two small spheres. I'll bring this up close, and we see it doesn't have an effect on the electroscope, or at least a negligible effect. The other one, as I bring up, also is neutral and has no net charge on it. Next, what I'd like to do then is to charge up the Van de Graaff generator. And if we charge that up, we've shown previously that the Van de Graaff generator, the top sphere, will pick up a negative charge, and we're going to put some excess electrons on that sphere. And in the process, we're going to develop a field, an electric field surrounding that sphere, looking something like this. So if we have a charged sphere with negative charge, we'll have an electric field in that space around the Van de Graaff generator. To demonstrate that field,
we haven't gotten to electric field yet, but we're going to be looking at that today. So
field. What I'd like to do is to bring up this uncharged sphere in that field. But first of all, let's charge it up and form that field. We're charging it to the point where the electric field surrounding it is strong enough to cause some electrical discharging. And you can maybe hear that popping sound of miniature lightning. but nevertheless, I now have a charge, a negative charge on that sphere. And to show the effect that it has on another sphere, when brought into that electric field, what it's going to do is that electric field is going to push the electrons from the near side of this little sphere over to the far side. It'll push the electrons from the side closest to the Van de Graaff generator over to the side furthest away. And if I set it there, then locate it close enough to where the arcing doesn't take place, but it's in the electric field where the field is strong enough to push electrons to the far side. And just to test whether that's the case, I'm going to bring this other sphere over here, make contact with this sphere, and let those electrons on this first small sphere jump over to the second small sphere, thereby charging this sphere up negatively, leaving this sphere charged up positively. Since this is charged negatively, the negative charge on this one came at the expense of taking electrons from this one, so this then has a net positive charge on it because it has missing electrons, those electrons now being transferred over to this one. I'm holding this with an insulated rod so they don't get transferred over to my body. Now, I take this positive charge over near the electroscope, and we notice the positive charge then attracts the electrons up to the top, taking electrons off the movable arm and letting that arm relax and come in closer to the fixed arm. So next I'd like to show that this sphere is charged negatively by bringing it over near the electroscope. By bringing it near the electroscope, it drives the electrons down. The electroscope, remember, is charged negatively. So as we drive those electrons down, this demonstrates that this has a negative charge on it. So this sphere is charged negatively. This sphere is charged positively. The charging of those spheres was done by the electric field of the Van de Graaff generator.
Okay, so that's charging things by induction. By the way, human bodies are pretty good at absorbing the small amounts of excess charge that are on these things. So you can touch something that's charged up and much of that charge will drain off onto you. There's also ground, which is if you have a wire or a copper rod driven into the earth and a wire connected to it, you can connect it to one of these things, and that ground wire will absorb excess charge off of things, either positive or negative. So that can happen too. So there's some kind of fun with these things anyway. Yesterday we just barely got started with solving problems with Coulomb's law, and I want to go a little farther with that today, and then we'll introduce the idea of electric field and go from there. And I just noticed this morning that this handout's available to you, but I don't know if I had the drawing in there or not in the handout for you. But I did notice this morning that I meant to have numbers on each of these p's as a subscript, and for some reason I made them as exponents instead when I was in the drawing utility and Microsoft Word. So that came out a little bit weird, but that's okay. Okay, anyway, the black dots all represent protons here, and so P1, P2, and P3, and we want to calculate the net force on P3 that's due to P1 and P2. And one thing I forgot to put on here was the actual coordinates of P3, but P3's coordinates would be 4.00 nanometers in the x direction and -3 nanometers in the y direction. And I picked those numbers so that we'd have a 3, 4, 5 right triangle. And that way I know the distance from P1 to P3 is going to be 5.00 nanometers. So I can use that. But the first thing I can do is calculate the force on P3 due to P2. That's pretty easy. These two things are going to repulse each other, and there will be a downward arrow here that'll be the force on 3, and I'll call it the force on 3 from 2. And so it'll just look like that, and I shouldn't have written that there because there will be another arrow along the line connecting those two. And I'm drawing the arrow way too long, but this would be the force on 3 due to charge 1. And so the net force on that thing is going to be the vector sum of those two, but we have to figure them out individually first, and then we can add them together. And the adding together won't be too hard. So the force on 3 from 2 is going to be KQ3 Q2 divided by the distance between 2 and 3, which is going to be, well, the distance is the distance, 3.00 times 10 to the minus 9th meters squared. And the direction of that is going to be in the minus j hat direction. So that's one of those forces. And we can plug in the numbers here and figure out all that stuff. And whoops, from 2. Okay, well, K is that 8.99 times 10 to the 9th. I'm going to write all the numbers up here because they're new to you still. Newton meters squared per Coulomb squared. And they're all protons, so Q1 equals Q2 equals Q3 is the charge on a proton, 1.60 times 10 to the minus 19th coulombs. And I haven't used that number since last spring, and I'm having to remind myself what it was. Yesterday, for a minute, I forgot what it happened to be. And after we've done a bunch of these problems, that number will just start coming to you kind of naturally, as will the K. That'll happen pretty quick. So I'm just going to plug in the numbers on this thing really quick and figure out what this is. It'll have a minus sign, and it's going to end up with a j hat over here. So just in case you forgot, I hat points in the x direction. J hat points in the positive y direction, but this will be in the negative y direction. So that's the minus sign there. Okay, and I get minus 2.56 times 10 to the minus 11th. Whoops, missed my decimal point. And newtons on there. Coulomb squared up here for the charge times charge, and that'll take care of the Coulomb squared and the K value there. And then meters squared on the bottom, we'll divide those meters squared, and we're left with newtons. So that's how that will work. Okay, now the F of 3 from 1, I'm going to calculate the magnitude of it first, and then I'll figure out the direction. So 3 from 1, and so no arrow on top of that, I'm just after the magnitude. It'll be K, Q1, Q3, or Q3, Q1, whichever way you want to do it, And the distance between those two, again, a 3, 4, 5 right triangle, it'll be 5 nanometers, or 5.00 times 10 to the minus 9th meters squared. And so I can actually just redo that previous calculation with a 5 down there in the denominator instead of a 3. And I get 9.21 times 10 to the minus 12th. Newtons. Okay, but that's just the magnitude of that force. I need to figure out its direction. And to do that, I'll figure out the value of this angle theta here, the angle that it's going to make with the positive x-axis, and theta is going to be the inverse tangent of the opposite side divided by the adjacent side. And they are nanometers, but the opposite side is going to be 3.00, and I don't care about the sine of this angle. I'll figure out the components by logic, I guess. Anyway, 3.00 nanometers divided by 4.00 nanometers. And the nanometers divide out. Inverse tangent of 3/4. And, whoops, I must be in radians. Well, wouldn't hurt, I guess. But I'll switch to degrees. I think most of this quarter will probably be using degrees, now that I think about it.
Mr. Ham, can you slide the paper down just a bit for a little second?
Oh, okay. Yeah, didn't know where I was there. All right, I get about 36.9 degrees. So here's what the actual vector value of that force is going to be. The force of 3 on 1 as a vector is going to equal that number, 9.21 times 10 to the minus 12th newtons, times, in the x direction, it'll be the cosine of theta. And actually, maybe I'll just draw a little triangle here to illustrate that. It's going to point in this direction. So it looks like that, but we've got this angle theta here. This will be the x component, 3 on 1 comma x. I know we're a little rusty on this stuff. This will be the y component, f3 on 1 comma y. And this one, the x component divided by the magnitude, is going to equal the adjacent over the hypotenuse, so that's the cosine theta. So we'll just take the cosine of theta in the I hat direction, and this is going to be negative, pointing in the negative y direction, so I'll just have minus the sine of theta in the j hat direction. So that's the way I figure these things out. I don't trust the punching negative values into my calculator because I don't do it often enough to have faith that it'll give me the correct answer. And so I just deal with positive angles and figure out the signs by looking at the geometry of the situation. So what I'd end up with is, and I'm still going to be after the sum of these two, but that value times the cosine of 36.9 degrees, which I think I'll store here. So I get 7.37 times 10 to the minus 12th I hat minus, let me just do it with the sign of that thing, .53 times 10 to the minus 12th in the j hat direction. Okay, so those are the individual forces here. Whoops, there's that one. And the sum of those two, the vector sum of those two, is going to be the net force. Well, there's only one component in the I hat direction. Whoops, I forgot units on these. Good grief. What a mortal sin that was. Anyway, I caught it. So, but the I hat component won't change. The j hat component will be this j hat component from that j hat component. And I hope you can follow that. So F net, the net force on that thing, is going to be 7.37 times 10 to the minus 12th newtons in the I hat direction, minus the vector sum of those two, and I'll need to do that by hand. And I end up with actually 5.53 added to that. I ended up with 2.56 times 10 to the 11th, which is what I had in the first place. I should have gotten something more out of that, unless I put in a wrong number somewhere. Did anybody else get that? I don't know. I'll try it again. Oh, I know what happened. I put in a positive exponent on one of them. There we go. That's better. 3.11 times 10 to the minus 11th newtons in the j hat direction. Okay, so that's the net force. That was kind of a lot of work to do, but we haven't dealt with I hat and j hat notation for a while, so it's kind of good to reintroduce it. Now, what about the magnitude and direction of the net force acting on P3? Well, the magnitude of it, F net, these two things are at right angles to each other, so it's just going to be the Pythagorean sum of those two, if you want to think of it that way. But it'll just equal the square root of 7.37 times 10 to the minus 12th newtons squared plus, and I know that's negative, but when you square it, it's not going to matter, times 10 to the minus 11th newtons squared on that one. So the magnitude of the net force will equal And I get about 3.20 times 10 to the minus 11th, so newtons. So there's the net force. The angle it's going to make is not going to be this 36.9 degrees. I need to figure it out a little bit, but it'll equal, if I make yet another sketch, I could call this angle phi now, and it'll be 3.11 times 10 to the minus 11th in this direction, and 7.37 times 10 to the minus 12th in this direction, and it'll be the inverse tangent of these two, and it'll be an angle clockwise from the positive x-axis. So that would be a complete description of it. So inverse tangent of that should work. And I get 22.9 degrees. So phi equals 22.9 degrees CW from plus x-axis. So there's a complete not a very legible complete description of that direction by having that. Okay, that's kind of complicated doing things like that. We're not often going to do stuff like that. Once in a while on the first test, I'll have you calculate the force, magnitude and direction and I hat, J hat components from a single charge, but not two. It gets kind of cumbersome after a while, and it's just kind of a pain. So, however, let's do one, add a layer of complication to this thing, quite a layer actually. And this is a continuous charge distribution. You have an insulator in the shape of a thin cylinder, and it has a uniform distribution of charge placed on it of 6 times 10 to the minus 15th coulombs per centimeter. And so that means if you pick any particular chunk of length of this thing, doesn't matter where it is, it's going to have the same amount of charge on it as long as that thing is the same length. We often use the letter lambda for charge per unit length. Let's see. We'll use lambda for charge per unit length. I think we tend to use sigma for charge per unit area, and then rho for charge per unit volume if we're doing something over a volume. So anyway, here's our first use of this. We've used lambda for wavelength before, but here it'll be charge per unit length. And lambda happens to be 6.0 times 10 to the minus 5th coulombs per centimeter. Oops, that should be an uppercase C. But I'm going to multiply that by, let's see, 100 centimeters per meter. And I'll get lambda is 6.0 times 10 to the minus 3rd. 100 is 10 squared, and if you multiply 10 squared times 10 to the minus 5th, you get 10 to the minus 3rd coulombs per meter. And so that way will be metric. And then we've got this, the cylinder is 15.00 centimeters long, which would be 0.1500 meters. And this distance is 5.00 centimeters, which would be 0.0500 meters. But I'm going to call this L for the length of the charged part. and this distance here, A, for those 5 centimeters, so that I don't have to write down numbers much. Okay, now, something we know is Coulomb's law, that the force on something is going to be K Q1 Q2 over R squared, and that's just the magnitude of the force. So we want to know the force on this electron due to this positive charge distribution that's on here. First, think about some conceptual stuff. What direction is that force going to be? Okay. All of this is positive charge. This is negatively charged. Opposites attract. And so the electron is going to have a net force in the negative direction. But maybe we can not worry about that until the tail end of this thing. Now, because this is a continuous charge distribution and it's of varying distances, we may want to just leave things in variable form for a while. I think I'm going to let my coordinate system start over here at the left end of this rod. So there's my x equals 0. And I'm going to consider little chunks of this rod. Now, this is something that when we start using integration for things, as we will have to do on this problem, it's best to work stepwise on this. And so I'm just going to imagine some chunk of this rod that has a length dx. And so dx is going to be the length of this little chunk of rod. And I'm going to imagine that it is a distance x away from the origin. And so that's kind of sloppy, but this is going to be x right here. Okay, it's the distance from the origin out there to where my chunk of charge dx happens to be. All right. Well, how far is that chunk dx going to be from our electron? Okay. The electron is at a position L plus A, and so L plus A minus x will equal this distance. And so for us, R is going to equal L plus A minus x. Okay. And try to work that through logically. This is something that's kind of tricky to get the hang of. Okay, well then, what about the charge on our little chunk here? We know that the charge on the electron is just minus E, but I'm going to call Q sub E, the charge on the electron. That's our minus 1.60 times 10 to the minus 19th coulombs. The charge on our little chunk of element, which I'm going to call dq, d lowercase q, is going to equal, well, it's got a charge per unit length of lambda, and it has a length of dx. This is another tricky part, okay, to somehow figure out the charge that's on some little incremental length of this thing. And this is something that we'll do several times, is have a charge distribution that's spread along the length of something, and we'll want to figure out the charge on little tiny lengths of it. And so that's what we've got here. And now, instead of F, I'm going to talk about a little increment of the force that's due to that little tiny length of it, and I'll call it dF, and it will equal, by the way, I'm not working with vectors here because this is a one-dimensional problem, and so I know which direction the final force is going to be, but I can figure it out from the sign of the force actually. So that's why I'm working with scalars here, but it'll be dF will equal K dq times Q sub E divided by my R squared, but R was this thing, L plus A minus X. So, and I'm going to reorder things here. Q sub E dq over R was L plus A minus X, and I could have done another simplification here. I forgot. dq is actually lambda dx, and so I'll have K times Q sub E times lambda times dx. Okay, so here's K times the charge of the electron times the charge of our little chunk of stuff there, and I divide by L plus A minus X. And that's, whoops, that's supposed to be squared. All right, well, what's our variable here? K, Q sub E, and lambda are all constants, so they're not variables. L and A are both constants. And the only thing that changes as we go all the way along here is X. So we managed to somehow get an expression where the only variable in it is X. And this is something that's kind of tricky. Sometimes you can set problems up and you'll end up with several variables in it, but you need to somehow get them down to being just one variable. And we'll try to do enough problems so we familiarize ourselves with that. Okay, so let's integrate. The total force that's going to be acting here is going to be the integral of dF, okay, over that whole charge thing, but we can deal with that. Well, that integral is going to be the integral of this, and I'll have K Q sub E, that's the charge on the electron, times lambda, that's the charge per unit length on this thing, just a number, and dx divided by, let's see, all that stuff, L plus A minus X quantity squared. And what about my limits of integration? Well, I want to integrate over the entire length of this charge so that I take into account all of it. Well, X is 0 down here and X is L up here. So I'll just go from 0 to L. And there's my expression. Now, when you're integrating, anything that's a constant can come outside the integral, at least if it's multiplying it. I'm going to have to do some thinking about this, but 0 to L of, whoops, I forgot to pull them out, K Q sub E lambda 0 to L of dx divided by L plus A minus X quantity squared. All right, I am not all that sharp on my integrals anymore, but seeing something like this, I think I'm going to change variables because I'm not so crazy about this. So I'm going to let U equal L plus A minus X, and then I'll imagine du is going to equal minus dx. And when x is equal to 0, u will equal L plus A. When x is equal to L, those are my limits of integration, u will equal, well, I just stick an L in here and I'll get L plus A minus L. I'll get just plain A. So my integral that I had there for the force is going to equal, whoops, K Q sub E lambda, an integral that goes from not from 0 to L, but from L plus A to A, which is kind of weird, And then instead of having a dx up here, I'm going to have a minus du. Remember, if du is minus dx, then dx is equal to minus dA. And on the bottom, instead of having L plus A minus x squared, I'm just going to have u squared. Now, I can fix this. We're usually not too fond of having things like this, or not. Just pull the minus sign out front, I guess. I can do that. Minus k q sub e lambda. And now I've got the integral of du over u squared, which I believe integrates to minus 1 over u. Does that sound right? Tell me if I made a mistake.
Should be minus 1 over u.
Yeah, and I evaluate that, and I could never keep track of where you have parentheses on these things and all that other junk, but I'm going to evaluate it at L plus A and A. And so let's see. Yeah, that should be okay. A minus times a minus is a plus. I'll get k q sub e lambda, and then I'm evaluating 1 over u, which is just at these 2 points. So I'm going to have 1 over a minus 1 over L plus a, which, let's see, I can play around with k q sub e lambda. If I multiply top and bottom of this one by L plus A, top and bottom of this one by A, I'll have L plus A minus A over A times L plus A. This is something like what we did last quarter when we were playing around with the image formation by lenses. And that ends up being just L over A times L plus A. So K Q sub E lambda and L over L, whoops, A times L plus A. Okay, now are the units going to work out? If I look at this, I've got my constant, which is Newton meter squared per Coulomb squared. So Newton meter squared per Coulomb squared. And I'm going to imagine that I've converted everything into meters on this. The Q sub E is going to be coulombs. Lambda is coulombs per meter. Here I'm going to have meters over meters squared, because I'll have length on top and length times length on the bottom. And some of those meters will divide out. Here I'll have coulombs times coulombs, which is coulombs squared. That'll divide with those. Meters squared over meters squared, those will divide out. And so I'll end up with newtons, and that's good because it's a force that I'm supposed to be ending up with here. And so there's our first integral of the quarter. And I don't know if the technique I used on here is something you do in calculus. I think that's called a U substitution or something like that. It's been a long time since I actually used a first quarter calculus book for something like this, but that's the way I tend to do these things and not have to look up an integral any more often than I absolutely have to. So now at this point it would just be a matter of plugging and chugging on this thing. So whoops, that's a noisy phone. Wow, it's getting through a solid core door. Let's see, KQE. Oh, I don't know why I was dealing with that side of the paper. Anyway, KQ sub E lambda times L over Oh, and if I hadn't turned this piece of paper up, I could remember what these things were. A was 5 centimeters, L was 15 centimeters. So let's do it. 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. There's K. Q sub E is minus 1.60 times 10 to the minus 19th coulombs. I should have been going sideways on this thing. I will. 8.99 times 10 to the 9th Newton meter squared per Coulomb squared. Charge, God, I'm still running out of room. Oh well. Minus 1.60 times 10 to the minus 19th coulombs. And then lambda was 6.0 times 10 to the minus 3rd. Coulombs per meter. And it was 10 to the minus 5th in the problem, but that was coulombs per centimeter, and I fixed that. And then I've got this little geometry problem here, which is going to be wherever it was, L, which is 15.1500 meters, divided by 0.0500 meters times 0.200 meters. So I've got 4 sig figs on this part, but I've only got 2 sig figs elsewhere. So I'll end up with 2 significant figures. And this is just a multiplication problem now. But that minus sign on here tells me my force is going to have a negative sign, which I knew from the start because this is an electron and this is a positively charged rod. So it'll be pulled back in that direction. And this may be scary. You might want to watch this part a few times if you're unfamiliar with applying integration to physical problems, which I think they do a little bit of in calculus, but not enough as far as I'm concerned. Anyway, several times this quarter we'll be integrating things to figure out the result when you've got things like continuous charge distributions or a current in a wire that might be a long straight wire or a curved wire or things like that. And actually, for the end of the unit on magnetism, we'll also be taking derivatives of things because there's a relation that shows up having to do with the derivative of something late in the unit on magnetism, and it's a connection between electricity and magnetism. Okay, for the lab this week, I think I'm going to have to run out to school this afternoon and gather some data for you, and so I won't have that data until after I've done that, and I'll take a bunch of pictures with my camera to show you how I'm gathering the data. We're going to be doing something that will be determining the resistivity of a couple of different types of metal. And this resistance is something that comes out of resistivity. And this should be in the chapter on DC circuits, but tomorrow we'll look at this, but you may want to read chapter 25, which is a little bit about current. And these are things that we're not going to study in lecture, but we're going to be dealing with in the labs this quarter. So current, and then talks a little bit about some interesting ideas, and then resistivity, is section 25.2, and resistivity and resistance are the things that we're going to be dealing with in this laboratory. And the digital multimeters that I had you buy will measure resistance. We're going to take a series of resistance measurements to determine resistivity. But last year I thought I'd be teaching live labs by this point, but I bought an accurate ohm meter, is what it's called, and it'll measure the resistance of something to much greater precision than the ones you have, Will. And that's not a problem most of the time, but for determining the resistivity accurately, we want to measure the resistance of some things more precisely. And I'm actually very tempted. Out at school, I've got some, well, those, actually, you never dealt with them. I've got some aluminum rods, and I can measure the resistance of those things fairly accurately, and we could figure out the resistivity of aluminum too. I've got some coils of wire that are some copper ones and then some other metals too. So that's what I'll be doing today, is gathering the data for that. But if you want to take a look at just the first 3 sections of chapter 25, and you don't need to read it heavily, the thing particularly you want to pay attention to is the resistivity and resistance. So that'll be the lab for this week anyway, once I gather that data. Otherwise, you do have a homework assignment up there, and I'll see you tomorrow on that. 1, 2, 3, 4, 5, 6, 7. Hey, everybody's here today. Okay, please.
Mr. Ham,
Yes.
Could you go over that problem, just a quick review of it that you
Which
just
problem?
did?
Oh, the
Like
integration? Okay. Let's see. Well,
you share your screen real quick.
oh, yeah, I need to go back to whatchamahoots. There it is. Okay, man, I take a couple weeks off and forget how to do everything. Anyway, here was the problem, and this is on the handout. I think the book, I don't know if they do any examples with integration right off the bat or not, but they should be. They might be doing it for electric field, which will be starting tomorrow. But got an electron here in this positively charged rod, and the problem is that the rod is not a single distance away from the electron. And so we have to figure out the contribution to the force from a tiny part of the rod, what it'll be on the electron, and then figure out a way to add up all the contributions from the different parts of the rod. Well, here's what the force was due to a tiny part of the rod. dq was the charge on that tiny part of the rod. R was the distance between that tiny part of the rod and the electron. And I had to figure out how to do that with the parameters we had in the problem. We were given the charge per unit length on the rod, and that lambda ends up being, I could think of it as being dq divided by dx, actually. This isn't exactly a derivative you would do. It's dq here is the little bit of charge on that little bit of rod, and dx is the length of that. And if I divide the charge divided by the length, I get charge per unit length. And so that's what lambda is. But that's how I got to dq equaling lambda dx. And that's something that's a bit of a leap and something that people struggle with. But a lot of times we'll be given the total charge on something like capital Q and divide it by the total length of the thing, and that'll end up being the charge per unit length. And so we might do something like that, but then if you wanted the charge on any other smaller length, you would just divide dq by the smaller length. And so that charge per unit length might be a bit of a conceptual hurdle. The other part that was a little bit of a leap in here was figuring out this distance r in terms of the things we were given in the problem and the variable that we made up called x, which was the distance along the rod we were. So those are things that you may want to watch that part again and try to see how that stuff works. I'm going to redo this problem tomorrow, but not with the not calculating the force on an electron. Instead, we're going to calculate the electric field that this rod produces somewhere out along the length of it. And I'll also do it, maybe not exactly this one, but I'll do it in a way where we'll modify the geometry, where we may not stay on the axis of this thing, but we might go above it or below it, and see how that works. So this isn't the last time you'll see this particular geometry.
Okay, thank you. That makes a lot more sense.
Yeah, we'll visit it again. Okay, let's see. Oh, something I'm going to do is post something that will let you set up an account with OpenStax, which publishes an OpenStax University physics book. And then you can, it's a free way to set up an account with them, by the way. And you can have that OpenStax physics book as an additional resource for example problems and maybe alternate explanations of things. And once you've set that up, you can do stuff like highlight parts of the book. You can write notes for yourself in there, and they'll be saved. So if you go back and look at that part of the book again, you'll still see your notes in there and things like that. I'm kind of getting converted by this idea of the online textbook, although I still like to be able to write and scribble in the margins of my textbooks. And I don't know how easy it would be to reproduce some of the mathematics and save that in notes to yourself in an open source thing. But anyway, I'll be doing that later today too. So other than that, I've got class in 10 minutes for my next class, so I'll have to turn you loose here. See you tomorrow.